All right.
Awesome.
Without further ado, today's marked speaker is Sandra Nair.
Nair, yes.
Nair, talking to us about intersection of Ekedahl-Oort strata with the supersingular locus of q-2.
Shimura Varieties.
Shimura Varieties.
Yes. Well, thank you so much for having me. This is really a practice talk for one that I'm supposed to give in about 3 weeks' time. So I really appreciate any constructive feedback audience members might have. So let me begin by saying that my talk is based on a project that was done with the Rethinking Number Theory group in the summer of 2022. We are still continuing on with the project. I'm here to present some new results beyond. The title of my talk is on intersection of Ekedahl-Oort strata with the supersingular locus of general unitary Shimura varieties of signature q-2, comma 2. I'm not expecting you to have prior knowledge of what those terms mean. I hope it becomes clear as the talk goes on. So let's get started. The motivation for this topic comes from an age-old question that is to do with elliptic curves. In particular, we're going to consider elliptic curves over an algebraically closed field of positive characteristics. So let's fix a prime P, and we're going to consider elliptic curves over FP bar. The main question here is, can we establish a dichotomy on these elliptic curves based on whether they are ordinary versus whether they are supersingular? This is a familiar classification problems over, let's say, elliptic curves over C. So it turns out it could be extended for positive characteristic as well. So here I'm going to note down some equivalent criteria for what it means for an elliptic curve to be ordinary. So the first criteria, and this is the one that will be most relevant to us for the other aspects of the talk, is that if I look at the P torsion of the elliptic curve and look at the FP bar points of the P torsion, this should give me a group scheme that's precisely Z mod PZ. Equivalently, I could say that the P rank of my elliptic curve is 1. Another way of thinking about this is that the endomorphism algebra over FP bar of my E is an order in a quadratic imaginary field. And lastly, but this is something we will come back to, another way of thinking about it is looking at the Newton polygon of the P divisible group associated with this elliptic curve, and that Newton polygon has precisely 2 slopes, 0 and 1. So maybe I'll just write that NP of E looks something like, suppose I have this set up, 1, 2, 1. So for the case of ordinary elliptic curves, I might get something that looks like that. So slope 0 and slope 1 precisely. Okay. On the other hand, what happens when we are dealing with supersingular elliptic curves? So I'm going to look at the same criteria, but for the supersingular side now. So the first one is looking at the P torsion group scheme. So here it turns out to be trivial, or just the identity, if you will. The P rank of E is 0. I should write yes. If I look at the endomorphism algebra over FP bar of E, this is an order in not a quadratic imaginary field, but in a quaternion algebra. Quaternion algebra. And finally, if I look at the Newton polygon associated here to the P divisible group, it should look like, okay, here here's 1, here's 2, here's 0, here's 1. So it should look like this. So in other words, it has slope 1/2. I hope that the, oops, sorry, 1 second. Yeah, I hope it's visible. Yeah. Questions, comments, thoughts?
So the question?
Yeah.
How is the thing on the left a polygon? Isn't a polygon supposed to be convex?
Oh, that's because number theorists take they kind of take a different convention of drawing it. I think if you were trying to translate into more standard ways, you might want to do it like that instead.
Oh, okay.
Yeah. It's just the convention used is that the more close you are to being supersingular, you're considered smaller slopes, and the further away from that, you're considered larger. And to emphasize that, they drew it in this manner.
So should the polygon be a trapezoid on the left and a triangle on the right?
Sure. Yeah. I'm not going to fill that in because this is usually the standard way they represent it. But I hope you get the idea of what's going on. All that's really important here is that the associated slopes for ordinary case is 0 and 1, whereas that for supersingular is 1/2. Great. So now the question we could ask ourselves is, how common is the ordinary case and how common is the supersingular case? So this is almost like an arithmetic statistics problem. And to answer this question, one good thing we can study is the moduli space of elliptic curves over FP bar. So what's a moduli space? We can think of a moduli space as a topological space with bijection, with a certain bijection on it, in a way that every point of the topological space parametrizes some isomorphism class of the object that we're trying to study. So in this case, we can consider a space Y. Let me see if I can use a laser. Where's the laser? There it is. I think that's a laser. Yeah. So in this case, we can consider this topological space Y. And this topological space is supposed to classify elliptic curves over FP bar. So it turns out that there's a very nice candidate that helps with this classification, and that is FP bar itself. The way it works is we can take an elliptic curve, as given by this Weierstrass form over here, and send it to its J invariant. The J invariant is this somewhat complicated looking expression over here. It's just an algebraic expression involving a bunch of integers. An important thing to note is that once I plug things in, I'm going to get something that lives in FP bar. It's just a number living in FP bar. So for every elliptic curve, we can uniquely send it to its J invariant, and that established the arrow from right to left.
So
and yes?
Assuming that the characteristic is not 2 or 3 here?
Oh yeah, sorry. Maybe I should have mentioned this in the beginning. Yes. Thank you for pointing it out. We don't want to deal with a singular case. So let's take P not 2, 3. Well, I'm going to allow 3, but for the case of the elliptic curves that we are just talking about, it's a nice case, not 2 or 3. Thanks for pointing that out. Right. And it turns out that we could also, given a particular algebraic integer in FP bar, so given an integer in FP bar, we can send this to a unique elliptic curve which gives us that J invariant. So this is a bijection, which was the criterion we had to begin with. Now that brings us to the next point. Somehow this topological space must be able to distinguish between these ordinary and supersingular elliptic curves. So we want to rewrite the space Y as a disjoint union of Y1 and Y2, where Y1 corresponds to elliptic curves which are supersingular. So I can go with the first criterion of what it means to be supersingular over here. And the second one corresponds to elliptic curves which are ordinary. Now, geometrically, what can we expect something like this to look like? Well, it's going to look something as follows. Most of the things, turns out, are going to be ordinary, most of the elliptic curves, and then some of them are going to be supersingular. So this is FP bar. I have color-coded FP bar for the blue to represent the ordinary case of elliptic curves that they're parametrizing, and the orange to represent supersingular case. There's a famous result by Eichler, Maas, During, which says that the number of these FP bar points is the number of supersingular elliptic curves for a given prime P is approximately P by 12. That's an asymptotic result. So this is kind of the picture that we are hoping for. But now the question is, what does a picture like this look for higher dimensional generalizations of elliptic curves called abelian varieties? So what would such a picture look like when we are dealing with abelian varieties? So in this case, we could be asking ourselves the question, let's consider the P torsion of abelian varieties over FP bar. What are the group schemes we expect to encounter here? So I'm going to see if I can color code this. Maybe it's G1, G2, G3, so on and forth. It is finite, I will mention that. So that's the question, and that's the general setup of this problem that we're trying to study. Can we generalize the classification result we have for ellipticals for higher dimensional abelian varieties? Now let us start with the setup and the statement of the result we had in this project. But first, let's establish some definitions. I did say that at the end of the talk, maybe the terms in the title would be clear. So let's fix a quadratic imaginary field denoted by capital K or kappa and a prime P that is not 2, which we want to be unramified in K. You can take the prime to be inert if you like, but whatever I'm saying could be generalized to the split case as well. Then what we call a general unitary Shimura variety of signature AB, let's see, so here, which we're going to denote with mathcal M A comma B. It is a solution to a moduli problem, just like FP bar was a solution to a moduli problem. And in particular, it parametrizes a tuple of information, A, iota, lambda, and eta. And what those stand for are as follows. So it parametrizes abelian varieties of dimension A plus B. These abelian varieties come equipped with an action of an order in that fixed quadratic imaginary number field. Oh yeah, maybe I should just write number field here, just to be very precise. Yeah. Lambda is a polarization, which you can think of as a group homomorphism going from an abelian variety to its dual with certain extra criteria associated with it. And eta is the level structure here, which we will not be talking about anymore for the rest of this talk. For experts in the audience who might worry about such things, we're going to assume that this eta is hyperspecial at the prime P. And in particular, we want these structures to be compatible in a certain manner. And what that means is we want something called the Rosati involution to hold. The Rosati involution is ensuring essentially that the polarization plays well with the action. What that means is if we have any automorphism in our quadratic imaginary number field K, we want to make sure that the map that takes an abelian variety to its dual, the polarization, and the action respects that automorphism. And that means that this particular square has to commute for any alpha in K. The other criterion that must be satisfied is the determinant condition. It reads as follows here. All that I want you guys to take away from here is that the A and the B that we saw in the signature, those are dimensions of eigenspaces coming from the action of our order in the quadratic imaginary field. So that's what we call the signature of the Shimura variety. It's just the dimensions of eigenspaces of an action. Okay, so now where does that bring us? I will use the following notation here. FP bar. So when I write something like this, what I mean is I'm looking at these tuples, and in particular, I am looking at these tuples over FP bar, and I'm looking at their isomorphism classes. So the isomorphism has to respect all these extra structures. It's not just a group scheme isomorphism, but it's a group scheme isomorphism which also commutes with a bunch of other stuff. And it turns out that the dimension for some Shimura variety of signature A comma B is precisely AP. Any questions so far? Comments, thoughts? Okay. Well, then let's move on. The other part of the title that kind of stuck out is this concept of Ekedahl-Oort stratification. So the definition is as follows. If I have two such tuples of information given here, so a tuple associated to an abelian variety A1 and that associated to A2. So these two lie in the same Ekedahl-Oort stratum by definition if they are isomorphic as p-torsion group schemes in a way that the group scheme isomorphism is compatible or commutes with all this extra structure. So in other words, A1 and so in other words, two abelian varieties A1 and B1 with all these extra stuff, they lie in the same Ekedahl-Oort stratum if their p-torsion group schemes are isomorphic. There is a fancy type of isomorphism between them. There is another way to stratify our Shimura variety because that's what we are doing. We are partitioning it into disjoint sets on the basis of these p-torsion isomorphism classes. Instead of looking at the isomorphism classes of p-torsion group schemes, we could instead look at isogeny classes of the p-divisible groups associated to these abelian varieties. So this tuple corresponding to A1 and that corresponding to A2, it is said to lie in the same Newton stratum, that was not actually mentioned in the title, if the p-divisible groups associated to them are isogynous to each other in a manner respecting all the extra structure. And the stratification on the basis of Newton strata can also be thought of as stratifying on the basis of the underlying Newton polygons of these various p-divisible groups. Why did I mention that? Because it turns out that a very special case of the Newton strata is the lowest dimensional case, which is also the unique closed Newton stratum. And it turns out that the unique closed Newton stratum parametrizes those tuples A iota lambda eta where A is supersingular. And that is why we call it the supersingular or the basic locus, and it is denoted by MAB with the superscript SS for supersingular. Yeah, and it's also the lowest dimensional Newton stratum in our case. So now I think we have set up pretty much most of the definitions given in the title. We know what Ekedahl-Oort strata are, we know what the supersingular locus is, and we know what Shimura varieties of a certain signature type is. Okay, how are we doing on time? Not bad. All right. So now we can ask ourselves I will mention one thing here. It turns out that the dimension of the supersingular locus is the floor function of AB by 2. So thought I will mention that. So that brings us to the next part. We can ask certain questions now. For example, how do these two stratifications interact with each other? And in particular, how do the Ekedahl-Oort strata interact with the supersingular locus? And finally, what is the geometry of the supersingular locus? These last two problems are of special interest to folks who study the Kudla-Rappaport program. Enthusiasts, maybe I'll write that. So that sets up the general motivation of why we are trying to answer this question. For the sake of addressing the different Ekedahl-Oort strata we might encounter, I'm going to introduce a certain labeling system. I'm just going to refer to them by gamma xt. It doesn't really matter too much precisely what the definition of gamma xt is. The thing that I'd like you to take away is that the dimension of the stratum associated to gamma xt is precisely given by 2x plus t. This will be relevant to us as later in the talk. So it's just a labeling system for labeling the different strata. Now let me start by saying some known results for the questions that I asked previously. When we are dealing with the case of signature of the form 0, q, and I'm asking what does a supersingular locus look like, it turns out that it is 0-dimensional. In other words, it's just going to be a disjoint union of a finite collection of discrete points. In the case of signatures, say 1, something, we have a result by Wallard in 2008, which says that if we consider a sufficiently small level structure, each irreducible component of the supersingular locus is in fact going to look like a Fermat curve. So if you're wondering what that might be, consider the following curve. P plus 1, x1 to the p plus 1, plus x2 to the p plus 1, living inside p2 of fp bar. So each of the irreducible components are going to look like Fermat curves. Plus, there are PQ plus 1 intersection points on each irreducible component, and each intersection point is the intersection of P plus 1 irreducible components. So this is a very combinatorial setup, which justifies why I'm speaking in the seminar today. Vollard and Badon, in fact, gave a theorem that says that the supersingular locus is precisely the disjoint union between those intersection points and those Fermat curves. And I'm going to attempt giving a small doodle of what this might look like. So pretend for a moment that this background in blue is a dimension 2 Ekedahl-Oort stratum. So the Fermat curves, say it looks like something like that, with I'm not doing a good job with this, but hopefully it should be fine. Okay, let's see. So these green dots are supposed to be my intersection points. And I'm trying to etch out the geometry of what's happening. I'm not going to be more thorough than this. So there are PQ plus 1 of these green intersection points, and each on each pink line that you see. And there are P plus 1 pink lines in question. So according to the result that's just given, the supersingular locus is the union of this whole thing. Okay, let's see. And so on and forth. So one thing that I'd like you guys to note here is that in this case, the supersingular locus is the union of two different types of Ekedahl-Oort strata. That's the case for signature 1, 2. So another thing about these Ekedahl-Oort strata is that they have some kind of topological closure relations, in the sense that if I look at my green dots, they lie within the topological closure of the pink lines. The pink lines are disjoint from the green dots, but they have this topological closure relation. And same thing between the pink lines and the blue dimension 2 strata. So what's going on is that the dim 0 EO strata, this lies in the closure of dim 1. And similarly, the dim 1 EO strata lies within the closure of dim 2. And that's another reason why we use this notation. We use these purple arrows to denote these topological containment relations. So I've tried to color code here as well. So gamma 2 zeros, did I do this right? 0, 2, 2, 0. Yeah, it should be fine. They have this kind of a setup going on. And this type of a result could be generalized whenever the minima of the A and the B is given by 1. Howard and Pappas generalized it a bit more in 2014 when they considered the case of signature 2, 2. So here, it's a morally similar result. So in this case, the irreducible components are again given by Fermat curves, but one dimension higher. Living inside P3 FP bar. And they also said that any two irreducible components are going to intersect either trivially or in a projective line or in a point. So pretend that these are two of the degree 2 stuff. So they're saying that either the intersection is precisely given by these green dots, or maybe I'll just try to do another here. it's going to be a projective line, and maybe some green dots line in the projective line. I hope that's visible. So it's my attempt at capturing the statement here that, yeah.
The green dots, are they like separate points?
Yes, they
So
are.
do you mean in points, or because you said or in a point?
Oh, I see, sorry, grammatic confusion or in, yeah, sure.
Okay.
Thanks for pointing it out. I shall clarify. In points, yeah. Oh, maybe I should clarify a little. Okay, let me try to do it this way. I'm saying that if they don't meet in a projective line, they meet exactly in one point. But if there's a projective line involved, then there might be multiple of these green points lying in the projective line. So I wasn't sure how to write that.
Embedded points.
Sure, yeah. So it's, as you can see, the complexity has gone up a lot compared to the doodle we had up above, right? And the result here says again that in fact, if I look at the supersingular locus, it's still the union of these three things, which is pretty nice. And using the, this is supposed to be a 0 over here, yeah. And then again, using the result from earlier, and I meant to write a 1 here, not a 2, doesn't really matter, but okay. And then we can again represent this using our labeling system of strata. The blue ones correspond to dimension 2, the pink one for dimension 1, the projective line, and the dark green for the dimension 0. And again, we have those topological closure relations between them. So in general, you'll note that the complexity goes up as the minima of A and B goes up in our signature GU A comma B, right? So now our work was trying to address what was not addressed in the Howard-Pappas case. When we have signatures of the form q minus 2 comma 2 for q greater than equal to 5, then what does all of this look like? And that brings me to the main result we have. So this is, I mentioned that this was from the R&T group, so it's joint work with Devang Pamadipati, Maria Fox, Heidi Goodson, Steven Gruen, and Emerald Stacy. We were able to classify exactly which Ekedahl-Oort strata of signature 3 comma 2, general unitary Shimura variety, intersected the supersingular locus with the help of our indexing system. And moreover, we found the first explicit example of a stratum that intersects the supersingular locus but is not contained in it. And that brings me to why this case was a lot harder to do than some of the previous cases. I mentioned that the complexity increases a lot as we look at higher and higher signatures. And in particular, both the cases mentioned above had this property that if my Ekedahl-Oort stratum intersected the supersingular locus, it must be fully contained in it. The moment we leave behind signature 2 comma 2, that is no longer the case. We have cases where it meets but does not live in it completely. And that means the geometry is going to be a lot harder to describe. So this is the main result we have, and we have some other results as well for higher signatures, but this is the one that I wanted to talk about today. So I highlighted I filled in orange bubbles for those which intersect the supersingular locus, and I left them blank for those which do not intersect the supersingular locus. Okay, so in particular, this time our supersingular locus is no longer the union of Ekedahl-Oort strata of the lower half dimensions. So that already makes it a lot more interesting. So now let me mention a little bit about the techniques that we used to make to get this result. So working with p-torsion group schemes directly is extremely hard. The way we get around it is by using certain categorical equivalences and translating our problem into a more pliable setup. So the first thing we did is to go from the language of Ekedahl-Oort strata to the language of mod p Dieudonné modules, which can be represented combinatorially with these objects called Kraft diagrams. So suppose I stick with one of the special case of gamma 2, 0, which I mentioned above. So suppose this is the strata for gamma 2, 0. It's going to correspond to a mod p Dieudonné module, and that is an algebraic setup, an algebraic expression of the following form, where f and b, they are you can think of them as Frobenius and the Verschuebung operators. If you're familiar with mod-PDUND modules, this might look similar to you. Familiar to you. Equivalently, I could also use Kraft diagrams to represent this, and that's going to look something as follows. 1, 2, 3, 4.
Can you was Kraft KRA?
Yes, what I'm drawing right now is an example of a Kraft diagram. Think of it as a diagrammatic and combinatorial way of representing the same content that is captured by this algebraic expression. So somehow I'm saying that there's a categorical equivalence between these p-torsion group schemes and setups of this form. Once we're in this land, we can actually do linear algebra and get a lot of nice results. But sometimes that's still not enough, and we need to travel further using and use the corresponding Weil group coset representatives. For practical purposes, they just look like some product of permutation groups that sees the signature. So it's going to look something as follows for this particular example. Times 4 times 3. So we don't have to go more into the details of how these equivalences work, but I'll just say that we're translating it into a land where it's easier to do computations. I'll also mention that there is a direct counterpart to the concept of containment in the topological closures. So topological closures here. There is a counterpart here with something called the Her partial ordering, which is a generalization of some of the more common in the literature Bruha partial ordering. So Bruha, I hope I got the name right. So the Bruha ordering, which is something that happens on Bruha-Ditz buildings, for example, is a combinatorial gadget, which has a generalization that corresponds to topological closures on Ekedahl-Oort strata. Okay, now in my remaining time, I'd like to talk about our overall strategy of how we manage to classify these strata into whether or not they intersected the supersingular locus. And it involves 3 main approaches. The first one is using the forgetful functor. So another well-studied moduli space in the number theory literature is something called the Siegel modular space, which can be thought of as a generalization of like the fundamental domain, for example, when you're trying to classify elliptic curves. So the way that you go from a Shimura variety to a Siegel moduli space, turns out it's pretty nice. It's in a way less complicated because recall that for our Shimura varieties, we were parameterizing this 4 tuple of information. What's going to happen is we will forget the endomorphism part. So if this corresponds to, say, stratum S, this will be phi S that we're going to. Why is this relevant? Well, it's relevant because there are certain tools and techniques that exist on the level of Siegel modular space that we could try to solve down here and then try to lift it back up to the level of unitary Shimura varieties. So there are 2 things that are useful here. One is if my stratum downstairs completely lives in the supersingular locus of my Siegel modular variety, then that means that the stratum upstairs must also live in the supersingular locus. And similarly, if my stratum downstairs is completely disjoint from the supersingular locus, it means that the stratum upstairs must also be completely disjoint from the supersingular locus. And from this, we were able to get results for 5 such strata using the first part of ruling in things into the supersingular locus. We got the results for gamma 00 and gamma 01, and using the ruling out result for the second one, we got for x3. However, this method is not complete. There is a problem, and the problem is there's no conclusion if the stratum downstairs is partially supersingular. In other words, it intersects but is not fully contained downstairs, then we don't really know exactly what went on upstairs. Maybe it just intersected, or maybe it was completely disjoint upstairs but collapsed into something downstairs. There is a way to fix this problem and still get some results out, and that's using two concepts. One is the concept of nilpotence of operators. So I mentioned this F and V above, the Frobenius and the Verschubaum. So it turns out that if you are a stratum who is contained in the supersingular locus, then your F and V operators need to be nilpotent on the p-torsion group schemes. So this is a way for us to rule out stuff, because if we find out that the operators are not nilpotent, you must have not been supersingular to begin with. So this is to rule out strata if the operators are not nilpotent. The other option that we can use is the so-called concept of minimal Ekedahl-Oort strata. Minimal strata have this following property, that if you are suppose you have A and B that lives in a minimal stratum T, this means that the p-divisible groups associated to A and B must be isomorphic, as opposed to isogenous. This is useful because it turns out that every Newton stratum contains a unique minimal Ekedahl-Oort stratum. So if you are an Ekedahl-Oort stratum who lives in a Newton stratum that is not the basic locus, so not the lowest dimensional one, then you cannot meet the lowest dimensional Newton stratum at all. So this helped us to take care of a few more strata in our list. That's the first strategy that we used. The second strategy that we used is the so-called concept of product maps. As I mentioned, the complexity of the Shimura variety goes up a lot as we look at higher and higher signature differences. So one thing we can do is try to break it down into factors of more understandable signatures. So here's what I mean by that. If I have a Shimura variety of signature AB and that of CD, I'm able to build out of it a Shimura variety of signature A plus C and B plus D, using this sort of a product structure, hence the terminology. So how does this method help us? Well, if our two abelian varieties A1 and 2 are both supersingular, then our product A1 cross A2 is also supersingular. The problem here is, you might have guessed by the sign of the implication here, is that it's possible that A1 and A2, the parent abelian varieties, need not be supersingular, and yet the product continues to be supersingular. So possible that A1, A2 not supersingular, still A1 cross A2 is supersingular. But using this method, we were still able to tackle a few such cases. Again, we are looking at signature 3, 2. So one way of splitting up 3, 2 is by splitting it as 2, 2 times 1, 0. And that way we were able to tackle these 4 cases. And finally, I'm now in the last method that we used. There were still 2 strata that avoided all our previous attempts. Oh, yes?
Something I don't understand. So the p-torsion of the product should be related directly to the p-torsion of each, right?
Yes, but in this case, it's not that simple, because we also need to account for all those extra structures.
I see. So the extra structure spoils the raw group theory.
Exactly. Yeah, if we are dealing with just the p-torsion group schemes, then you're absolutely correct. It decomposes perfectly, and you might the properties get directly inherited. But we have now this new endomorphism, a new type of polarization, and a new level structure also playing about.
And those can be skewed to
Yes.
yes. Spoil the people. Okay.
Exactly.
Thanks.
Yeah. So turns out there were 2 strata who managed to avoid all the nets that we cast at it, and that's those labeled by gamma 02 and gamma 20. So we had to explicitly try to tackle them. So in our previous cases, we were depending on prior knowledge of some other stuff and relating it to the Shimura variety. These 2 managed to avoid that. So we had to come up with something new. And here's what we did. We looked at the corresponding mod P Dewdnay modules, or equivalent in the Kraft diagrams involved. So they look very similar. The only difference between them is that for gamma 02, these two arrows are flipped compared to gamma 20. And turns out that makes quite a bit of a difference. So the first thing we did was to lift them to the level of p-adic duodenate modules. Mod p duodenate modules have a categorical or equivalence of categories with p torsion group schemes. P-adic duodenate modules have an equivalence of categories with p divisible groups. So the first thing we did was lift them into p-adic duodenate modules, which I'm going to try to keep the color coding to the best of my ability, so that I'm going to call M02 and M20. The next thing that we did is we inverted P. So now I'm looking at M02 adjoined with 1 over P and M20 adjoined with 1 over P. Now, why did we do that? Because turns out, upon inverting P, I get an object called an isocrystal. I'm happy to talk more about it later, but I'll just say that for now, it was nice for us to get isocrystals because there was a famous result we could use, thanks to Zink, Thomas Zink, is that given an isocrystal, we can actually compute the slopes of the corresponding Newton polygon associated to that isocrystal. So this allowed us to compute slopes, slope calculation. And what we found out was that the slopes of these particular lifts that we chose were both exactly half. But that means that our gamma 02 and our gamma 20, or the corresponding Ekedahl-Oort strata, must both intersect the supersingular locus, because from them we managed to obtain Newton polygons with the slopes half. And this was the recipe we followed to get that. I will mention that there was a secret ingredient being used because ultimately the question was about the existence of abelian varieties which are supersingular, and what we did in practice was compute p divisible groups which had that supersingularity property. So somehow we want to relate our work on p divisible groups to abelian varieties, and the secret ingredient here is called Rappaport-Zink uniformization, sometimes also called p-adic uniformization. Well, what does that say? Well, the result says that if we look at our supersingular locus, so let me just look at our own supersingular locus here, FP bar, then this is isomorphic to a disjoint union of Rappaport-Zink spaces. Modded out by some stuff. What Rappaport-Zink spaces are? Well, they have a somewhat simple interpretations. So over here on the left side, we have abelian varieties with endomorphism, polarization, and level structure. And we are saying that A is supersingular because that's what the supersingular locus is. Rappaport-Zink spaces similarly parameterizes a tuple of information, and that tuple is as follows. This G over here, that's a p divisible group coming from the abelian variety mentioned on the other side. So for points for a supersingular, iota and lambda are the same structures as on the left side, and this last item rho, that's called it's called a quasi-isogeny rigidifying structure. Not too important what it is. I will just say that we were able to construct this row, which was the last ingredient we needed, using a result of Warlard-Bedford. So we got this, we got these two, and we finally also got this. So once we had all that information, we could use the Rappaport-Zink uniformization to go from p divisible groups to abelian varieties, because that's exactly what we did. Over here, we had results for p divisible groups, and using Rappaport-Zink uniformization, we were able to translate that into abelian varieties, and therefore we managed to explicitly construct a supersingular abelian variety living in those two strata. And hence showing that those two strata also intersect with the supersingular locus. And that brings me to the last bit, which is what are possible future works. One of the things we are very much interested in is exploring more of the combinatorial aspects of the topological closure relations in the signature q-2, 2. Furthermore, we would also like to extend a certain classification result that exists for signature q-1, 1 to q-2, 2. We are currently developing this concept of indecomposable Ekedahl-Oort types, and that's something that promises to give us some new tools to tackle the geometry of the supersingular locus. And finally, and yes, we would also like to study the intersection of the Ekedahl-Oort strata with higher Newton strata. So far, we restricted our attention to the supersingular locus because that was of interest for folks in other aspects of number theory. But in order, as good mathematicians, we want to be as general as possible. So we would also like to study the case of higher strata. And finally, understanding the geometry of the supersingular locus. I'd like to share pictures of my collaborators here. So let's see if I can capture all their names at the same time. And yes, thank you so much for your attention. I'm happy to answer questions.
Questions?
So your focus on q-2 is because of the Rappaport signal?
No, it's because it is the next lowest hanging fruit available. So the Rappaport-Zing uniformization, that is more general. It is not restricted by signature, which is a really amazing theorem. We used it as the final ingredient we needed for our method of explicit construction. The reason we focused on q-2, 2 for q greater than equal to 5 is that, as I mentioned earlier, the geometry gets really complicated, and this is the case of 3, 2, for example, is the first case of so-called non-Coxeter Shimura variety, where Coxeter Shimura varieties are those Shimura varieties with the property that the supersingular locus is a union of Ekedahl-Oort strata, and that was the case for all previously studied works. 3, 2 and q-2, 2 for q greater than equal to 5 is where that property no longer holds. And so we wanted to tackle the case of, okay, let's try to understand at least the simplest cases of Shimura varieties which do not have the Coxeter type property. So that's why we focused on q-2, 2.
These Shimura varieties, are they in particular sub-varieties in the moduli space of all abelian varieties, or?
So sadly, there is no well-defined notion of a moduli space of all abelian varieties. We need to include polarization into it in order to make it. Yeah, sure. Yes. So that is exactly what's happening with this forgetful functor over here. So the Ziegel modular varieties that is precisely the solution to the moduli problem, asking to classify all abelian varieties with a given polarization and a given level structure. So a subvariety of that is precisely, that I don't know if I should use the word subvariety, but yeah, geometrically it is seen as a subvariety living in there.
Okay, so then my follow-up question is, if you take sort of a fiber product of that map with the Torelli map from NG bar, do you get interesting stuff in the moduli space of curves, like the strata, their way to intersect?
Yeah, thank you so much for that question. So I don't think I've seen, okay, so I know that Rachel, for instance, who's with us on Zoom, definitely worked on using unitary Shimura varieties in the case for moduli curves. Rachel, feel free to correct me if I said that wrong, assuming she's still there. And so yes, there has been studies done of okay, let's use the Torelli locus, and also let's also use a structure of unitary Shimura varieties, and that is some active research. That is an active research area right now. Yeah. So since you mentioned fiber products, I will mention that when I'm looking at these FP bar points, let me scroll up to where I wrote this the very first time. Yeah. So when I'm looking at these FP bar points, what I'm doing is I'm fixing an integral model of my Shimura variety, and I'm looking at the special fiber over P. So there's already an underlying fiber product going on. Yeah. And the reason why I insisted P is not equal to 2 is because when P is equal to 2, we do not have a well-defined integral model with this moduli interpretation for it. So yeah, in case that was something some folks were wondering.
Any other question? Questions from the Zoom audience? Right, then let's thank Sandra again.